All right, I think we're live. Okay, so hello everyone. Thank you for joining us and welcome to our online quantum chaos seminars. We're back for the fall edition. We have some great talks lined up for the coming weeks, so we're very, very excited about that. As usual, let me just remind you, how this works. Today, as usual, we have you'll be seeing the talk through the live stream, and you have the opportunity to contact us and most importantly the speaker through the live chat to ask questions and make comments and just say hi, whatever you want. And for the questions, we'll just take them to the speaker in the middle of the talk if you want, but mostly at the Q&A session at the end. Right, so today we are very excited to welcome Alvaro Alhambra from Max Planck Institute for Quantum Optics. Alvaro's research interests cover many topics, including equilibration and thermalization in quantum many-way dynamics, and thermodynamic resource theories, among others. Alvaro got his PhD from University College London and was after that a postdoc at Perimeter Institute, and he has very recently joined Ignacio Sirac's group at the Max Planck Institute as a postdoc as well. So again, Alvaro, thank you very much for joining us today. We are very excited to have you here, and take it away whenever you're ready.
Okay, well, thanks a lot, Pablo, and also Peter for the invitation. It's great to be able to give an online seminar like this, in this setup. And it's a great, I think it's a great resource to have, like in general in the scientific community, all this business of like online talks that you can watch after and so on. So hopefully mine is also useful for people. Okay, so just to start with the talk, well, I have this title that you've probably seen before already: Equilibration, Eigenstate, Thermalization, and Linear Response, which is just 3 different things that are of course related, and hopefully, the title is a bit vague, but hopefully I can make it more specific as we go along. Okay, so this work is in collaboration with Jonathan Riddell and Luis Pedro García Pintos. Jonathan is a student in McMaster, and Luis Pedro is a postdoc in Maryland. And yeah, actually, I really want to highlight the recent work of Jonathan, who's been doing really nice numerics for this project. So all the numerics you see have been basically stuff that Jonathan has done. And so much of what I'm going to say is already published. It's in the archive, and also we published it in PRL earlier this year. And another part of it is in progress still. Maybe in the months to come, we'll see. Okay, so let me just start with the business. First, actually, I guess I want to give a bit of an introduction to a couple of terms that I'm going to be talking about, which Pablo already mentioned. So I guess one is equilibration and another one is thermalization of quantum systems. So the setting in which I'm going to be focusing is that in which you have a unitary evolution of your quantum system, which is given by a Hamiltonian. And Hamiltonian is of this form. It's basically a local Hamiltonian with like local terms acting on very few sites. And in general, you're going to have a geometry in your lattice, which is, for instance, like a chain. Yeah, and basically you have unitary dynamics. And a very interesting problem is one in which you actually evolve a pure state. So you have some initial pure state and you evolve in time, and you want to see how how it evolves in time. So there's a couple of interesting questions you can ask. One of them is the question of equilibration, which is the question of give me some observable A and the time evolution for time t. After what time t big does this number, basically expectation value, start looking like some fixed expectation value of some equilibrium sample. So at what point basically this quantity equilibrates in the sense that it sort of stops changing, and it reaches a fixed value. So this is the question of equilibration. And then there's the second question, which is following up on that, which is the question of thermalization. And that's the question of, given that you're already equilibrated to some ensemble, well, what is this ensemble? And in particular, is this ensemble a thermal ensemble, like a given state? So are these averages you get the same averages you will get for a given state? So these are very interesting questions and very rich. Probably, yeah, there's no fixed answer to all these questions, and probably many of the talks in this series have focused on some aspect of these things, But actually, I encourage you to look at these couple of reviews, which are already a few years old, but they're still very, very relevant and very interesting. Okay, so now a bit more about the setting. So of course, in my title, I had the words linear response, no? And the reason is because I'm going to talk about a particularly, I guess, a different instance of this problem. No, it's different in the sense that we don't talk about pure states, but we talk about mixed states. So I like to think of this problem of correlation functions as a slightly simplified version, no, of the problem of equilibration. No? So I'm going to be focusing on these quantities, no, which are basically 2-point correlation functions, dynamical response functions, you name it. No? So you have two observables, A and B, and you evolve one of them in time, and you take the thermal average. No? So this somehow is telling you about the following thing. No? You perturb your system with observable A, and this perturbation spreads around the system. No? And this quantity basically tells you about how does this perturbation look like to observable B. No? I mean, this is a big thing. No? But, and I guess this can be made quite precise, no? And in particular, if you look at the classic papers by Kubo, then this is very well explained, no? What this means exactly, no? In this context of linear response. But in any case, what I can tell you is that these are very relevant quantities, in particular for regimes which are sort of perturbations around equilibrium. No? Okay, so perturbations around equilibrium as opposed to things that are very far from equilibrium, no? Like this pure state evolution, for instance. So what I'm going to be talking about. So I'm going to be talking about a couple of different things. The first part of the talk is going to be about analytical results about the time evolution of these functions, which are going to apply to non-integrable systems, which, I mean, this talk, basically non-integral and chaotic are going to be more or less indistinguishable terms. No? And then after this, I want to just speculate a bit and show some results about the relation of this problem of far from equilibrium from the previous slide with this problem of linear response theory. You know? Okay, just a quick outline before we move on. So the analytical results that I'm going to show are basically nothing very surprising, but some of them we can show as theorems, basically analytically. You know? So the first one is that this 2-point correlation function converges to this other thing, which is basically, you know, it factorizes. No? So this is the product of the thermal averages of the two observables. No? So this is some sort of dissipation that occurs after the unitary dynamics. No? Another thing we can show is that actually this does not only happen in the large time limit, but it happens somehow for most times. No? So if you take this quantity to be like the average value, then the actual variance around this average is very small. This we can also show. And the other thing we can show is that actually this for autocorrelation functions, which are somehow a special case, no, where A equals B, then we can show that this actually happens in a relatively short amount of time. No? So these are the results we have of these functions, and then we're somehow going to take these as ideas, and then we're going to see how much they can tell us about this other problem, no? The problem of this quantity. No? And I guess this idea of linking this to this is not new. No? It's appeared in a few different papers. No? And I guess these are probably the most relevant that I found in the literature. No? And in particular, this paper was Rednicki. I'm going to be talking about it quite a bit in the second part of the talk. No? Yeah, so I'm definitely coming back to this one. But now let's just start with the analytical results. And actually, first of all, maybe I want to start with a bit of a technical assumption, no? Which is, again, is technical, but I think it's interesting that it's worth stopping in it for a bit. So the base for this, the main idea for this result lies on the assumption, which is the assumption that the thermal states have a finite correlation length, no? On the lattice. No? So this is a very standard assumption, and most thermal states obey it. This is well known. And the assumption is the following. Now you have a 2-point correlation function in which notice that there's no time. No? So this is just a spatial, you know, X and Y are just spatially separated. No? And they're spatially separated by a distance, which is this number here, distance. So what I'm saying is that this function decouples at large distances. No? So when the distance is very large, then this is basically equal to this. No? So this is what it means to have a finite correlation length. So the interesting thing about this assumption is that by itself, it implies quite a lot of things. And in particular, one thing that it does is that it constrains the thermal distribution quite a lot, actually. So from this assumption, we can infer that the thermal distribution, the Gibbs distribution of the thermal state, obeys something called a large deviation bound, no? Or something that looks like a large deviation bound. And this takes the following form. So I have this number here, no? And this number, what it means is basically the probability that the energy of the thermal state, so this is a trajectory in the energy eigenbasis, is far away from the average by some number, no? And some number that is relatively large, no? So this is somehow the tail of the Gibbs distribution, no? The tail that is far away from the average, no? So what this statement is telling me, and this particular statement comes from this paper by Anuraganshu, is that this tail is bounded by this number, which is exponentially small in n being system size, no? So for a very, very large system, no, this tail is super, super small, no? And as you can see in this picture, no, you have the whole bulk of the of the Gibbs distribution, and you have the tail, and basically this gray region, which is the tail, is exponentially suppressed in system size. And this is a very interesting fact, and one reason why it seems very interesting is because you can actually link it to something called the weak ETH. So what is this? So this is a weaker statement of what most people know as the ETH, no, or as the strong ETH, as I will call it. No? So the statement is about these numbers. No? So you have an observable A, no? And you want to evaluate this observable on a particular eigenstate, which I label as K. No? So this number is the expectation value of A on a particular eigenstate. No? So part of ETH, what it tells you is that all these numbers are basically equal to the thermal average, all of them. No? I mean, all of them all of the eigenstates that participate in the thermal ensemble are equal to the thermal average. No? So the weak ETH is weaker in the sense that it tells you that most of them, not all of them, obey this property. No? Or you can understand that most of them, or that with high probability, this is closely the case. No? So there's a very nice argument by Mori, which basically tells you that this weak ETH statement follows from large deviation bound, like this one from the previous slide. No? I'll talk about it in the next slide a bit more. And the one interesting thing about this weak ETH is that it's quite weak, no? And one reason in which you can see this is because it's actually true for systems that don't necessarily thermalize, no? So there's some interesting examples. In particular, it seems to hold for integrable systems. This was explored in this paper by Biroli et al. And also for these systems that many people are excited about nowadays, which are these systems with quantum scars, no? Which generally obey ETH, but there's some eigenstates which are these quantum scars that don't obey ETH, no? And actually, there's a nice example of these scars in this paper here, which is this graph that I showed you in this corner. No? So this graph is from this paper. So they look at this Hamiltonian, and they look at the eigenstates of this Hamiltonian, and in particular about the expectation value of some observable on those eigenstates. No? So these are basically the statistics of these numbers. No, if that makes sense. No. So basically, you can see that changing the parameter means that these peaks get bigger and bigger. No. So the usual ETH basically corresponds to this one here, in which essentially the peak gets, it basically is super peak, no? It becomes like a delta function almost in the limit, no? But of course, there's other regimes, like when you have these quantum scars, no? Where you're going to have eigenstates which basically give you a tail that is still small, no? So I mean, here, of course, the tail is bigger, no? But it's a tail that is still small, and in particular, it decreases with system size, no? So what the weak ETH tells you is basically it bounds the weight of this tail, no? And the second statement is the following, actually. So this statement that I'm going to be talking about now is from this paper by Brandao et al., which basically is putting together the argument of Mori and this other result by Anshu from a couple of slides ago. No? Okay, so it's a theorem, so it has some assumptions. No? So the assumptions are the following. The Hamiltonian is translational invariant on n sides. The thermal state has exponentially decaying correlations with some correlation length that is finite. And also an important one is that the observable A has a small support. It has support on order 1 sides. No? This is important. Okay, I'm going to show you the result for 1D, but actually it works for any dimension, and it's just a bit more cumbersome, the expression. So this is the result. So what is this? Okay, so it's a number that's bounded by another. Okay, so what is this number? No? This is a probability, and it's the probability of the following thing happening. You take the thermal distribution, and you start sampling eigenstates from it. No, so what this means is the probability of sampling eigenstate Ek from rho beta. No, so you can ask the question of what is the probability, given that I sample from the thermal distribution, that this expectation value is far away from the thermal average by an amount delta. No? So of course, if this delta is very large, you expect this to be very small. No? And in particular, this is bounded by this number. No? So this number is basically exponentially small in system size and also in delta. No? So you can see that basically what this is telling me is that the probability that I sample an eigenstate from the Gibbs distribution that is far away from the thermal average is exponentially small in system size, very small. No? So basically, most of the eigenstates are in the Gibbs distribution, no? That participate in the Gibbs distribution. This number is very close to this number. No, that's their property. No, so this is basically the basis of what we need. No, and actually now I can maybe quickly show you the proof of this result. So again, we have the same assumptions as before, and we have an extra one which is important, which is that the Hamiltonian is non-degenerate. No, okay, so maybe let's just start. So basically, what we want to study is this quantity. No. Which is basically you take your 2-point correlation function and you take the average from 0 to t, and you take t to infinity. No? So the point of this quantity is that if this quantity equilibrates to something, it's going to equilibrate to this late time value. No? So this is somehow the number that for sure this quantity equilibrates to. No? So we want to understand this quantity. No? This is basically what I mean with the late time value of this 2-point correlation function. No? So you can just write it out, and basically it's a thermal average. These are the Gibbs factors. No? and you have all these numbers that I was talking about in connection to the wiki.th. And you can just do some manipulations. No, you introduce an error delta, which is the difference between this and this. You use span. No, and so basically what you want to show is that this is equal to this up to some small error. No, so the point is you want to bound this quantity. No. Yeah, so just proceeding. No, basically, some of these terms are 0. You get only this one, and now you have two different contributions. No, basically, and you can separate them. No, you have a contribution in which the difference is large, and larger than some quantity that I'm not telling you what it is, but it's just some quantity that you have to fix for the bound to work. And then some other terms in which this delta is small. No. Okay, so now what is the argument? The argument is that given wiki.th, the probability of large fluctuations, so delta being large, is actually very small. No. So this already tells you, oh, like this factor is going to be small. And also, if you choose this delta star to be not very big, you can also bound this thing. No. So basically, if you put all the numbers together and sort of make the bound work, you have to choose this number accordingly. What you can get is this. Basically, that this is equal to this, which is what we want, the product of the expectation values at the thermal ensemble, and the error goes like 1 over n. So you can see that basically it vanishes in the thermodynamic limit. No? So in the thermodynamic limit, you can show that this is equal to this, basically. And this is already some notion of some weak notion of ergodicity, if you like. No? Let me just restate this again. No, basically this is the result. And actually, one thing I want to notice with this is that, again, people identify this with some notion of ergodicity in a sense. But of course, this is very weak, no? Because we only rely on the wiki.th plus this other assumption, which is the non-degenerate eigenstates, no? And eigenvalues, sorry. So actually, you can make the case that this kind of dissipation happens if your system doesn't always thermalize in the sense of the first slide that I showed. No? So this is somehow the difference between strong and wiki.th. No? Like the wiki.th already implies this, but the strong ETH, implies this plus other things, no, that are stronger. No? Okay, so hopefully this is clear, and hopefully I make the case that this is like an interesting result, no, because it's telling you about this dissipation that happens basically just from unitary dynamics, no, because this dynamics is unitary, no. Okay, so now I just want to have like a more complete picture of what this means, and for this we have another result, which is about the average size of the fluctuations around this value. Okay. So now take this leg time average value, which is what I've been talking about in the previous slide, no? And now I want to look at the fluctuations around this value. Okay. So now I take this quantity now, which is 2-point function minus the leg time average. I square it, so it's like a variance, no? And I average over time, and I take the limit, no? So this is basically the difference between this and this over all times, no? So if this number is very small, then this means that for most times, this quantity is extremely close to this one. No? So this is what we can show with some extra assumption now. So the extra assumption that we have is an assumption that is actually very generically done for this like chaotic or non-integrable many-body systems, which is the following. You have an energy gap, which is given by two energy levels, J and K, and you have another energy gap, which is given by L and M. And the assumption that we have is that if the energy gaps are equal, then it's because the energy levels are equal. So this is usually called the non-degenerate energy gaps condition. No? And this condition is basically generically quite well obeyed by systems with ETHs. No? And if this is the case, then we can show the following, that these fluctuations are bounded by this number, which is like the purity of the thermal ensemble. So this is a very, very small number. And in particular, it's actually smaller than this thing. And what is this? This is the equilibrium free energy of your thermal ensemble. So this actually grows linearly with system size. So this number decreases exponentially with system size. It's very, very small. And these quantities A and B are, of course, they're not very large. No? They're at most like polynomial in system size. So basically, what this is showing is that these fluctuations are exponentially small in system size. And actually, not only exponentially small, but you have this equilibrium free energy coming up here, no? Which is nice. And if you're familiar actually with these papers by Linden et al. And by Peter Reimann, basically they have an analog result for the equilibration problem from the first slide. No, so this is somehow and here instead of the equilibrium free energy, you will get the inverse participation ratio or the effective dimension in these results. So this is somehow the linear response analog of these results, no, if you like, which I think is also interesting because these results I think they're pretty nice. Okay, so that's it for these fluctuations. So now actually I want to show something else, which is about the timescales, no? Yeah, 1 second. Okay, so I guess one thing I haven't really covered. No, I've been taking in the previous slides. I've been taking these limits of t goes to infinity. No, but of course, t goes to infinity is a bit of an unphysical limit. No, So what you would really like to know is what happens for finite times, no? For times that you can actually measure in the lab, no? So of course, the behavior of this function is going to be quite rich. Like the finite time effects are going to be quite interesting, no? So you're going to have like, I don't know, maybe diffusion effects, things like this. So there's going to be time scales that depend on the distance between the observables, you know, like given by the Robinson bounds, no? Also system size, maybe, no? So one important question you can ask is basically how long does it take for this thing to become this thing, no? Like what is the dissipation time, no? So we can actually say something for this particular case in which A equals B, no? The autocorrelation function, no? Which we think is still quite an interesting particular case, no? Yeah. So the idea is that basically we're gonna prove an inequality like this, no? This is basically the same expression as the previous slide, but now I don't take the infinite time limit, no? And so the idea here is that we're gonna be bounding this by a function which depends on t, no? And basically how fast this function decays is gonna tell me how fast this thing becomes this thing, okay? Because the fluctuations around the mean value are going to be very small, no? For like a time that hopefully is not very long, no? Yeah. So basically, with this expression, what I want to capture is the following. So I have this graph which basically represents the behavior in time of this function, no? For different system sizes. You can see that the fluctuations decay with larger system sizes, no? As consistent with this thing. Yeah, so what I want to capture is basically a time scale in which this number is very small. And basically this number being very small means that big T is already somehow far away from this initial peak, in which is the initial peak in which you basically go to the equilibrium value, no? So I want to consider a big T here in which this number is very small, meaning that, you know, I'm already in this region of basically noisy fluctuations, no? Because basically these noisy fluctuations don't contribute much to this integral, no? Making it very small, no? On average. Okay, so this is the result we have. So we can bound this quantity by this number. Okay, so I need to explain a bit what this means. First of all, there's a couple of terms, no, with this one and this one, no, and of course the time dependence is here, no. It's like 1 over t, big T, no. So there's a few constants, no. There's first of all, there's this a and this delta, no, which I'm not going to define what they are because it's a bit cumbersome to define them. But basically, I need you to believe the following. No? We have these numbers here. And these numbers are basically the Gibbs states, the Gibbs distributions, and these numbers, which are basically the diagonal elements of B as written in the energy eigenbasis. No? So ETH tells you about these numbers too. So what I want is these numbers to be very smoothly distributed and with not too many degenerates in the spectrum. No? And these basically are very reasonable assumptions whenever ETH holds. No? So if this is the case, then it is highly expected, no? And you can argue this quite well, and that this number is basically of order 1, is not too large, and that this number you can basically make it arbitrarily small. So there's a parameter epsilon, no, that you have to choose, and basically you have to choose epsilon small enough that this is not very large and this is very small, no. So this technique was actually, I guess it was first, this kind of quantity was first developed in this paper by my co-author Luis Pedro. So this is the reference. Okay, so basically once you have these two things, no, true, you're left with this other number, which is sigma b, no. So the idea is that if this is true, then this sigma b gives you the time scale of your equilibration process, no. And this we have a close form expression for this number, no. It's very nice. So it's this. This is somehow a variance, no. So you can see that basically this is like a slightly complicated combination of things that are basically local expectation values, no. So this b is local, and the commutator with h is local, no. So this is like a very reasonable quantity, no. It's like it doesn't grow with system size or anything, no. So this is quite nice. Yeah. So basically, if these things are true, then it is the case that this is the relevant time scale for equilibration of your correlation function. And actually, one thing I want to notice is that these numbers are actually, I think we expect them to, to be good whenever ETH holds. But there's also some discussion about this, no. So if you look at this paper by Heveling et al, this reference, they actually explore some situations where, like, basically they look at this paper quite a bit in detail, no? And they explore some situations in which these things may not hold, and actually the situations have to do with like weak coupling and Fermi-Golden rule. So I think it's good to mention this to get a full picture of the whole thing. Yeah, so I encourage you to look at this reference and also this reference, and also of course our paper. No?
Alvaro?
Okay, yeah. So actually now, of course, I've been telling you a lot about these two numbers, no? But I guess I haven't really convinced you of that this is the case, no? So I want to give you now some numerical evidence, no?
Alvaro, can I ask you a quick question?
Yes, please. Yes.
So what do you mean weak coupling in the previous slide?
Oh, I guess I mean that Well, so for instance, you're looking at I don't know, you're looking at an observable, and the observable is in a region, no? And this region is coupled to the rest of the system, no?
Oh, okay, okay.
So in general, in the situations that I've been covering in this talk, no, it's basically a lattice model. So I will consider this to be strongly coupled, no? But I mean, I guess you can consider like I don't know, some sort of spin boson model or something like this, no? Where you have weak coupling between a system of interest and like the rest of the system, which is like a bath, no?
I see.
That's what I mean. I mean, to be fair, for all the details, I think you probably have to look at this paper. But that's more or less that's much of the idea of what they have. I mean, hopefully, I mean, maybe they can correct me if I'm wrong, the authors of this paper. Okay, so just to give you some numerical evidence of this. So we look at, of course, these numbers of A and delta, and so you can see some plots here. So you can see basically that epsilon has to be very small. So you should be looking at this part of the graph, the more interesting one, no? So basically, you see that as epsilon becomes smaller and smaller, this delta basically vanishes. It becomes very, very small. And at the same time, of course, you can see that sometimes from finite sets effects, this A can actually blow up. But of course, you can see that for larger and larger system size, such that basically this distribution is much more smoothly distributed, no? Then actually this A doesn't grow too much. So it stays constant at like 0.4, no? Which is like quite a nice number. No? It's definitely order 1. No? Yeah, so I mean, this is just a numerical example that we think shows that these quantities are well behaved. No? And one note is that actually, so we use the same technique at this paper, but of course, this paper looks at the harder problem of pure state equilibration. No? And I think in this case, the situation is a bit different. No? Like for us, all these quantities are actually a bit simpler. Yeah. And well, just let me mention that the Hamiltonian we look at is this one. It's like an Ising chain with like next to near neighbors couplings, no? And it's observable. No? Just for completeness, I mentioned this. And also another thing we do is we can look at the actual bound, no? How it performs, no? So we have this quantity, which is the one we want to bound, and we have the upper bound, no? So again, same Hamiltonian, which again is non-integral, no? Because you have this perturbation here that makes it non-integral, so ETH applies. And yeah, we have some numerics. Probably now we can get better ones actually, but they didn't make it on time for this talk. So the black curve is the upper bound, and the red curve is the thing we want to bound. No? So you can see that they're not very far, and also like maybe it's not super obvious from this plot, but actually it does get closer as you increase system size. So somehow we expect that actually this, I mean, basically the message in the end is this, no? So basically what I've been trying to convince you in the last like 20 minutes or so is the following, no? That there's a time scale which we can write down, no? Which is this. And for time scales that are much larger than this one, sigma to the -1, where sigma squared is this, then this correlation function does this, no? So it equilibrates to this value, no? So that's basically the conclusion of this section, no? As you've seen, many of these things we can actually prove, no? Like in some, yeah, I mean, with some rigor, no? Okay, yes. Now that we've learned this, all these things about the correlation functions, I guess what we wanted to do is basically explore if we can do something else with this, no? With this type of, with this type of result and with this type of function, no? And of course, the really big problem that we're interested in is the problem that I was talking about initially, no? The problem of far from equilibrium dynamics, and in particular of equilibration, no? So now, again, I come back to this setting, no, where I have a pure state that is evolving in time, and I want to look at the expectation value of some observable, no? And the question is, when does this thing start looking like the average of some fixed equilibrium ensemble, no? That doesn't depend on time, crucially. Okay, so of course, much has been done about this problem, no? But there's this paper I mentioned initially that I really want to highlight and bring up, which is a paper by Srednicki from '99, which I find like very, very interesting, and I encourage you to have a look at it. I mean, I've really been like trying to understand this in a lot of detail with moderate success, I have to say. But it's this title, no? The approach to thermal equilibrium in quantized chaotic systems, no? So okay, so let me tell you what this is about. So what this paper suggests is that one can sometimes model this quantity, which is a general equilibration problem, no, of a pure state, with some sort of 2-point function, like the ones we've been covering before, no? And this is given, but that the ETH holds. And now I'm going to be talking about not the weak ETH, but the strong ETH, no? Which is, I would say, is this equation here. So this is an equation that basically tells you about these numbers, which are the matrix elements of observable A in the energy eigenbasis, no? So there's two components, no? There's the case where J is equal to K, in which this is the relevant term. And basically this is telling you that when the diagonal elements look thermal, no? With some fluctuations. And when J doesn't equal K, then what this is telling you is that basically the off-diagonal elements are very small, very suppressed, somehow random, because these R, J, K are like random coefficients, no? And also crucially, they're very sort of like spread around, no? Like they're very, somehow the magnitude of the off-diagonal elements is very uniformly spread around the spectrum, no? This is what this is telling you. So actually this idea that I've been mentioning here, I think is also quite well studied in these two papers. So I really want to mention them. And I guess the thing about these papers is that the initial state is a bit more restricted, no? But they have some very interesting arguments, in particular in this second paper in connection with this ETH. Okay, so now I want to explain more a bit about this paper of Zrennicki, which I found really quite interesting, no? Okay, so again, we have this problem, no? Which is the problem of far from equilibrium dynamics. And now I want to write this quantity, which is the expectation value at time t of observable A, and I just expand this in the energy eigenbasis, no? So what does this look like? This looks like the following. You have this Cj and Ck, which are basically the coefficients of the pure state in the energy eigenbasis, right? So these are like the populations of your pure state. You have these numbers, A, J, K, and these are basically these numbers. The matrix elements of observable A as written in the energy eigenbasis. And then of course you have the time evolution given by these rotations. So given this quantity, what Zrennicki does is he defines the following two-point correlation function, which is very similar. It's not the same, but it's very similar to things I've been talking about before. No? So he's given us the following. No? Actually, the formal expression is this, where this bar, this average, actually indicates averaging over this time t prime. No? But the important thing is that this can be written as follows. It's proportional to this thing, which is basically, what you have here is basically a sum over jk, no? Over energy gaps, essentially. And you have Cj squared and Ck squared. These are basically these numbers squared, no? So they are the populations of your pure state in the energy eigenbasis, no? And now you have these coefficients, but of course the difference is that this is squared, no? So basically you can see that this and this are the same expression, except for the fact that this is squared, no? So basically the coefficients are positive, and actually this makes the quantity somehow a lot nicer to work with, no? And as I understand it from this, from what I was saying before, actually the fact that all these quantities are positive somehow indicates that somehow indicates that this is a correlation function, no? Because, for instance, in the two-point correlation function I was talking about before is basically the same as this, but instead of having these numbers, you have Gibbs distributions, no? But of course, this doesn't depend on a Gibbs distribution, no? Now it depends on some other distribution, which is given by a pure state, no? Okay, so the claim of Zrennicki is the following: is that after the system has equilibrated, if there is a large fluctuation away from equilibrium, then this holds. So basically the idea is the following. I have a little plot that I did with paint to show you what the idea is. And I did it with paint because basically we didn't find any example in the numerics. So this is the following. So you have A of t, which is a quantity that equilibrates and it stays here, right? It stays basically constant. And then at some point, because of recurrence theorems or other reasons, you expect that maybe there's going to be some sort of small revival, no? Not necessarily a whole recurrence, but a small revival, no? Like a large fluctuation outside of equilibrium, no? Because of course the system is not really equilibrated, no? It's not equilibrated like on average, no? But sometimes this is going to happen, no? So the claim of Zrennicki is that whenever this happens, this peak is actually very, very well modeled by this correlation function, right? Which is basically somehow like a linear response function, no? So I mean, I don't know. This is quite. I think this is quite a strong statement, and basically the whole argument is based on this ETH. Like if you look at this paper, it's very clear that this is the key assumption. The problem, of course, is that these large fluctuations, for this to hold, it seems that they have to be very large because this correlation function doesn't really model this noise. It has to be like a very large fluctuation, and basically the problem is that maybe these fluctuations are so large that you just never get to see them, no? Because they happen at like very, very large times, no? Like in physical, maybe, no? It could be that actually the revival that you need that is big enough, no? Happens at the time that it's exponential system size. No, we don't know this actually. It could be, I don't know. So it could be actually that this equation holds. I mean, it holds under some assumptions, no, but the assumptions maybe only hold for like fluctuations that happen at very, very late times, no? So somehow that makes it a bit less physical, no? Okay, so I don't know. So somehow I don't know, we put this a bit into question somehow, no, but we're still trying to find examples of this thing, of these large fluctuations, no. But still, I think there's some interesting idea here, no, because basically what is happening here is that you're defining a correlation function, which is dependent on parameters that are basically about your pure state equilibration problem, no. So the question we wanted to ask now is whether you can actually still connect the two things, no, even if not in this way, but in a similar way, no. So the question is, can this function, defined in terms of a pure initial state, serve as a tool to infer something about the actual dynamics, the dynamics of this quantity, no? Okay, so now we can actually apply the same tools as before for this correlation function, no? So we have very similar results, and in particular we have this bound again from the few slides ago, no, with the same constants. I mean, they're not quite the same, no? They're defined now in terms of these quantities instead of the previous 2-point function, no? But the idea is that basically we can prove in a similar way that this function equilibrates in a timescale that is given by this sigma f, no? And of course, now sigma f is a bit different. It looks like this, actually. And now you have this fraction of traces, no? So I don't know, this is a bit of a funny thing. It looks like a variance, but it's not because the state appears twice. So you have this d of the pure state, and basically what is this? Is this the diagonal ensemble, no? So this, you take the pure state, you dephase it in the energy eigenbasis, and then this is the state, no? So you multiply this with the commutator, and then again with the same state, and then with the commutator, no? And then you divide by this. And basically this quantity is proportional to this, which is basically the variance. So if you think of these numbers as parts of a probability distribution, this is basically the variance of this probability distribution over the energy gaps, no? So it's a very natural thing to consider, no, in this context, no? And actually, it's so natural that it has appeared before in the literature, no? So there's a couple of papers in which, in particular, this one by the Oliveira et al., where this quantity appears very clearly, no? And in particular, in these arguments, what they have is they analyze this quantity in the following way, no? You can think of this quantity as basically a sum of numbers in the complex plane that oscillate with different frequencies, no? So because they're oscillating with different frequencies, somehow this is going to be like a very large cloud in the complex plane, and it's very large and it's very random. So in the end, all these numbers are going to average to 0, and when they average to 0, you get equilibration, no? That's more or less the argument, no? And if you make this argument a bit more precise, which is what they do in these papers, you more or less can argue that the time scale in which this happens is actually this, which is somehow the variance, some sort of variance of these coefficients, no? So it's interesting that this quantity that appears from this argument also appears in this correlation function, no? So maybe this gives us a hint that we're into something, no? Okay. So so now we look at this quantity more in detail and see what it can tell us, no? So actually, the first thing we notice, and we notice this both numerically and with some analytical arguments too. I mean, it's not really a proof, but we have some analytical arguments for this. Is that at early times, so for t not very large, this quantity behaves like a Gaussian. So it decays like a Gaussian, okay? So basically the idea is that given ETH, all these numbers are effectively going to give you like a Gaussian, no? Given the randomness inherent to these coefficients, no? So this is going to be like the Fourier transform of a Gaussian, which is also a Gaussian, no? And just by Taylor expansion, you can argue that the variance in front of this Gaussian is actually this sigma f from the previous slide, no? So I think you can argue quite well that this function decays initially in time in this form, where this is the relevant constant, no? Okay, so now we can compare basically this decay to the decay in time of the problem we care about, no? Which is this. So this is what we do here. So we have some numerical experiments, and I'm just showing you an example, but this holds for like a very large number of basically everything we checked so far. This holds, no? So we have this Hamiltonian with this initial state, which is basically a linear combination of these things. No, I mean, the actual state is not terribly important. No, but I'm just showing it for completeness. Okay, so in this graph, what I show is the following. I have two curves, no, but I mean they're really four. But the thing is that this is a fitting with a Gaussian, no. So you can see the fitting is perfect. So this quantity here, which is this line, is basically the correlation function, and this other quantity is the actual value of the equilibration, no? The actual expectation value in time of the observable, no. Yeah, so you can see that they're both clearly Gaussian initially, no? This is something that is, basically we expect quite well, and the numerics tells us that the fit is really good, no? And yeah, you can see that very clearly that the expectation value of A of t decays faster than the actual correlation function, no? So basically what we try to argue is whether this behavior is generic or not, no? So what does this mean? basically, when you have the pure state equilibration, the curve looks like the following. No? So actually, now look at the dotted curve instead of the green one. The green one is the correlation function. So there's like a very early time decay, which is very fast, which is a very fast decay to equilibrium. No? And then there's going to be some noise on top of it. No? So we focus on this early time region, no, of the decay. No? And basically, this area here is basically this plot, right? And you can see basically this the initial decay is Gaussian. No? So the question we ask is basically we have this correlation function and we know it decays like this, and we have control over what this sigma is basically this number. No? So the question is, how does this constant relate to this other sigma, no? Which is basically a decay constant of the actual problem we care about. No? And basically what we've been finding so far, and we can argue on fairly good grounds, this is somehow still work in progress, but I think we can argue this quite well, is that basically one is faster than the other. So this decays faster than this. So basically the equilibration timescale of this quantity is faster than this number, or the inverse of this number. No, that's the main idea. No? So all the numerics show this, and also we have some analytical arguments for why this is the case. No, I mean it's not really a proof again. So this part of the talk is not as it's basically not mathematically rigorous like the first half. No, but hopefully I can still convince you of this. No. Yeah, so basically what we want to argue is the following, no? This sigma A is equal or larger than sigma F. Okay, so how do we argue this actually? So there's a few steps, no? So think that in the thermodynamic limit, this A of t is going to become a smooth function, no? So of course you can see that these fluctuations here, they're actually finite size effects, no? So in the thermodynamic limit, this is going to be a perfectly flat curve, no? That converges to zero, no? And also we know that for some early time, or at least the numerics indicate, and you can also make arguments for why this happens, no? That the early time decay is Gaussian with some constant sigma A, no? Okay. So the point is that under some conditions, if this holds, under some conditions, we can actually show that this is the case, that this constant is larger than this, meaning that the actual equilibration value, the actual expectation value decays faster than the correlation function, that we understand better, no? So for instance, it happens always whenever this number, when it's smooth, is always positive and convex, no? Or actually, more in general, there's this condition that is a bit technical, but this always holds whenever A of t is positive and convex, no? So just think of any decay that looks like this, roughly like this, no? So you can have a Gaussian, initially a Gaussian thing, and you can have some tail, which is also convex, no? Like some sort of also a Gaussian equilibration, or maybe like even a polynomial 1 over t, something like this. So any of these things. So basically, for any of these things, we can more or less show that this holds, no? That the early time decay, given this behavior of the whole function, the early time decay is always faster than the decay of the correlation function. No? And the argument is actually fairly simple. We just look at some expression, no? Which is, I mean, it's just like some function of this expectation value, no? And the good thing about this expectation value is that in the limit of t goes to infinity, this actually converges to the sigma f. So basically, what this expression gives us is a relation between the expectation value of A, no? A of t, and this other constant that comes from the correlation function, no? So basically, you can play around a bit with this, and you end up finding a relation between basically this limit and this other number, which is the one we care about and we want to bound. No? And I guess this expression we were inspired quite a lot by this paper by Oliveira that I've already mentioned. No. Yeah, so you can make some arguments for why this is the case. No. Okay, and I guess the other interesting thing about this correlation function that I've been talking about is the following. This was already like quite well discussed in the paper of Srednicki, but it's also very well discussed in this paper by Katami. No, and basically what this argument tells you that basically all correlation functions are pretty much the same, no, because of ETH, no. So now I'm writing this correlation function, which is the one I was writing before, no. And basically there's an argument given ETH that I'm not going to go through, but it's quite simple and it's well outlined in this paper, and also they check it numerically, no, which basically given that these numbers are over ETH, basically whatever is in front of here doesn't really matter, no? As long as it's like a somehow reasonable distribution that is peaked around the mean average of the energy, then this doesn't really matter, no? It's like in the same way that ETH tells you somehow that your actual population doesn't matter for the late time value, no? Because it's always thermal, no? Because since all the eigenstates are thermal, then of course the initial conditions don't matter, no? So this is somehow similar, no? Like whatever you have here, whether it depends on like Gibbs factors here in this function or like here, which depends on some other coefficients. Basically, these coefficients don't matter, no? For the time evolution, no. This is quite a surprising thing, but it makes sense once you think about it a bit. Yeah, so basically what this means is that this correlation function also behaves like a Kubo function, no? And also, and also you can make the case that this also behaves like the 2-point correlation function from the previous part of the slide, no? So basically, what I'm saying is that this correlation function actually decays like any other 2-point function, no? Or they all behave in a very similar way, no? So basically, this sigma f is basically a timescale of a decay of a 2-point correlation function, no? So in a way, in this guys, all that we're saying here is that somehow you're very far from equilibrium problem. It's always going to decay faster than your not so far from equilibrium problem, no? In which you have a perturbation away from equilibrium, no? So of course, far from equilibrium dynamics initially dissipate faster than the linear response regime, no? That's more or less the message, which I think probably something you can more or less expect. And actually, the one interesting thing is that these defacing arguments that I've been talking about before from these papers, what they actually end up arguing is that this quantity is roughly the same as this quantity. So I don't know, but to me, this indicates, all these arguments, it indicates that actually how far this is from this somehow depends on the initial conditions, no? So I don't know, one interesting thing would be to explore a bit more these arguments and see how they actually depend on how far you're from equilibrium, for instance. So like, do you expect this to hold more if your initial state is closer to equilibrium? No, I guess that's what I would say, no? Okay, so that's more or less the main message that I want to convey here, no? That we have some interesting relation between these two quantities, no? One of them far away from equilibrium, one of them more close to equilibrium, no? And I guess with this, I just want to summarize and conclude, no? So I've been telling you a few things, no? The first half of the talk was more about the analytical results of these 2-point functions, no? So we can show that this type of ergodicity holds, no? With an error that vanishes with system size. Actually, there's a typo here. This should be 1 over n, not 1 over square root of n. Also, the fluctuations around this average are suppressed by a number that is basically proportional to the e to the minus beta times the equilibrium free energy, so a very small number, exponentially small. And also that the time scale at which this happens for autocorrelation functions is somehow reasonable, no? And it's given by this sigma b that I was describing from a few slides ago, no? And the other thing that we explored here is basically the relation of this type of quantity, the sigma b, to the actual time scale that we have in more general equilibration problems, no? In particular, in this kind of thing, no? When you have a pure state that equilibrates, no? Yeah, so I guess an interesting question that stems from this is, basically to try to understand how these two time scales are related, no? Like for which kind of initial conditions or initial states you actually have that one of them is much larger than the other, no? Or when are they similar, no? I don't know. Hopefully, basically, in terms of like analytical results, like really no one really has a clue how to analyze this thing, no? So maybe this already gives you some sort of idea of how to proceed, no? Like try to compare this problem with the simpler and like less general problem of correlation functions, no? That's one thing I would like to like bring forward, no? As the message of this talk, no? Also in general to the quantum chaos community, no? And yeah, and with this, I just want to thank you for your time and for listening. And like this is the archive reference for the first paper. Hopefully we'll have another archive reference soon, but it's still in progress. And yeah, thank you very much. And thanks to the organizers as well.
Yeah, thanks a lot for this great talk, Alvaro, with a lot of interesting results. So a reminder to everyone watching, you can just ask your questions in the chat now. And there's already one question asking, how does the relaxation time depend on L, which is your system size, I presume?
Right, the system size, good question. Okay, so I guess you have to look at the expression of this, for instance, no? So I guess somehow the weird thing here that is almost magical is this doesn't seem to depend on system size. Because if B is local, like has like support on a few sites only, the commutator with H is also local. So this is just a local expectation value, no? If you grow the lattice, this is not going to grow. And none of these quantities are going to grow. So this sigma B seems to be independent of system size. What is not so obvious is whether this other quantity does not depend on system size. This I actually don't know. The only argument I have for the fact that this doesn't depend on system size is this point I was raising here, that somehow all the correlation functions look the same. So all the correlation functions should have like a similar time scale, no? So somehow this one that I showed you in the first slide that doesn't depend on system size clearly, maybe means that also this one doesn't depend on system size, no? But this is just a speculation based on this argument, no?
Thanks. That actually immediately leads to the next question, which is thank you for the great talk, and saying I may have the wrong idea, but shouldn't the thermalization timescale be observable independent, as it is an intrinsic property of the dynamics?
Observable independent. Oh, I see. Well, it's observable independent. I mean, I guess I'm not completely sure about this because, I mean, maybe there's some intuition for why that's the case. But for instance, I would expect it will be different in observables that are like local, meaning like on a few sites, and observables that are like maybe more extensive, no? That's an intuition. I mean, another fact is that maybe actually, if that's the case, maybe this is somehow hidden in these bounds, no? Because you can see that, I don't know, if you scale this A by a constant, then this constant is cancelled, no? So maybe it's true that this is roughly independent of the observable, but maybe the bound doesn't see it, no? So actually, I'm not completely sure. I would expect there's at least some slight dependence on the observable. But yeah, actually, I think there's some papers that analyze this. No, I think I remember there was a paper by the group of Sirac and other people where they look at some observables that always take very long time to equilibrate. No, so I feel like maybe you can always find observables that are exceptions. No, so maybe the bounds actually mean that they have to see this. No, so I guess I don't know. Maybe the intuition is correct, but maybe there's some complications with it. That's what I would say.
Okay, thanks. I also have a question myself, actually. So you had these two different timescales. Do you have some examples when the bound is exactly satisfied, when sigma A equals sigma F? Or
if I have some examples.
Actually, some examples,
I would say a very good example actually is given in these papers, in these two papers. So, well, of course, one example where this happens is basically when your initial state is not actually pure, but it's like a perturbation away from thermal equilibrium. No? Because, of course, in that case, the time evolution basically maps. You just do perturbation theory and it maps a two-point correlation function. But actually, these two papers have examples in which the perturbation is not weak; it's quite strong. So you perturb far away from equilibrium in a particular way, and it has to be a particular way. And actually, basically, this quantity or the analog of this quantity maps exactly a two-point correlation function. So that's examples, yes. Mm-hmm.
Okay, thanks. And then one additional question also from me. In your first bounds, you had this implicit dependence on beta. Do you have some idea what happens if beta either goes to 0 or infinity? What happens then?
Beta, sorry, in which part is the dependence on beta? Sorry? Yeah.
In the first, where you've also had this e to the minus beta f, for example.
Okay, so yeah, you mean like here, for instance, here?
Yes, exactly.
Right, yes, so I mean, I think this should, let me see. Yeah, how does it depend on beta? Right. Well, I guess probably, yeah, I would say probably as the temperature increases, probably this bound gets better and better. No, actually, as you can see, as the temperature increases, basically this ends up being 1 over the system dimension, no? which is pretty small. No, and I guess maybe as you go to lower and lower temperatures, maybe you expect I don't know, like you end up having to care about even your energy gap or something like this. No, so. Yeah, so maybe for very low temperatures, actually, this is worse. But actually, I'm not completely sure.
Okay.
I mean, in any case, this is always exponentially small, no? For like for any temperature that is like constant in system size, no? That is, I mean, basically, whenever you have a finite energy density, this quantity is going to be exponentially small in system size, no? And with some dependence on beta, yes. Yeah. Mm-hmm.
Okay, thanks a lot. And I think this concludes this week's seminar. So thanks again, Alvaro, for giving this talk and for answering the questions. Thanks again to everyone who's watching. And we'll be back next week with another seminar, this time by Samuel Garrett from the University of Oxford. We'll be talking about many-body quantum chaos and local pairing of Feynman histories. So see you then.
Thanks a lot.